Okay, so absolute value is a distance. There's some given information here. First of all, a real number has two qualities. A real number is either positive or negative, and then the other quality is the absolute value of the number. And so that is its distance from zero. Absolute value is not just the bigness of the number, it is the distance the number is away from zero on the number line. Since distance is always positive, then absolute value is always positive. Essentially what we just talked about, right? Now, we're going to look at example 1 and 2 here. And we're talking about graphing this set of numbers on a number line. And there's a couple of different ways we can think about graphing it. I mean, one of which is to work it out and solve it. And ironically enough, I was just teaching this in Algebra 2. Okay? There's also kind of a shortcut. And I'm debating, do I want to do shortcuts? How about we solve, and then I'll show you how the shortcut works, and then we can try it for the next one. Although the next one, of course, has a slight difference there, but yeah, exactly. Okay, so let's review what we remember, because solving it always works. Absolute value less than 2. Anyone helped any of my Algebra 2 students over the last 24 hours or so? Because we've talked about absolute value. With absolute value equations or inequalities, you get the absolute value by itself, and then you set up not 1 but 2. Okay? Not equal to 0, it's equal to the positive and then equal to the negative. In this case, because it's less than, we have to also change that sign. So my absolute value is the array by itself. I'm just going to set it up over here. The first one, you drop the absolute value but keep it as is. So x minus 5 less than 2. It's a less than sign, so I'm going to use the word nothing, less than, as opposed to greater than. It's an and or an or statement. If it's a less than sign, it's an and statement.
Oh my goodness.
Greater than sign. I just taught it in Algebra 2. I'm sure we reviewed it in pre-cal at some point, but that's probably been about a year ago also. So x minus 5 less than 2 and, no, still stays x minus 5, whatever's in the absolute value stays as is. Less than becomes greater than. Positive 2 becomes negative 2. Okay, so I guess it's a good thing we're reviewing how to solve this.
Yeah.
You do the basic solving, right? X minus 5 less than 2. Add 5, it becomes x less than 7. And add 5 on the other one, it becomes x greater than 3. How do I express this and statement as a compound inequality?
3 is less than x is less than 7.
Yeah. Where we put our x in the middle, larger number 7 on the right, smaller number 3 on the left, and when you put the appropriate signs, it's x less than 7, x greater than 3 ends up reversing, so 3 less than x less than 7. So that is equivalent to this absolute value statement. And we can graph that, right?
Number line.
Okay. How do I graph 3 less than x less than 7? Okay. Open circle at 3, open circle at 7, and you're shading in between. You can also look at it as x less than 7, so it's going left of 7. And, so we're going to overlap, x greater than 3, so greater than 3. So it's an open circle at both of them, shaded in between. Or if we're talking interval notation, it's parentheses, right? Excuse me. Okay. Can you connect this graph to this original problem here of absolute value of x minus 5 less than 2. What's the shortcut connection? Okay. So this 5 represents the midpoint, and then those outer points are how far away? 2 away. And so we've shaded everything that are less than 2 units from 5 is what we're doing. So if I put this in words, what this graph expresses, or this absolute value expresses, is all numbers less than 2 units from 5. And I don't know if you have to put it in words in the homework necessarily, but I just want you to make that connection. That, yes, we could solve this by hand, and we did. But we can also, you can also look at it pretty easily. Less than 2 is how far you're going from the center. You're going 2 from the center, and it's all numbers that are less than 2 units from 5. Whether that be 2 units to the left or 2 units to the right. It's kind of a handy little trick. Questions on that? Okay. Example 2. Now, the part that changes about example 2 is that 3x minus 1. But we can still do it. Trying to decide the best way to explain this. It is an or one. It is an or one. This is a greater than statement, right? So a less than statement was an and statement, and the shading went in. This is going to be a greater than statement, so my shading is going to go out. Okay. Probably the easiest way, because there's a coefficient of 3 here on the x. Divide that 3, because that 3 is going to have to divide by everything, yes? So if I divide that 3 by everything, don't think of this as a 1, think of it as a 1/3. Don't think of this as a 2, think of it as a 2/3. And so if we kind of try to compare what's up here, earlier it was all numbers less than, because they gave me less than. This time it's going to be all numbers greater than, because they're giving me greater than. It was less than 2 units here. Here we're going to say greater than, not 2, but 2/3 units from my midpoint of 1/3. That's what we're going to be graphing. Now, that graphing is a little tedious if you think about it. Let's see if we can graph it. We need to talk thirds, don't we? I did -1, 0, 1, 2, but if you can see my number line, I broke it up into thirds because we're going to be talking about thirds, right? So, let me write in words what we said, and then we'll try and graph it. All numbers, and this time it's going to be greater than, or I have written down more than, I don't care what you say. All numbers greater than or more than 2/3 units from 1/3. So, think about this. Where's my centering point going to be? At 1/3, which 1/3 is right here, yes? Nothing really goes there other than, I'm just kind of putting a little mark for my benefit. Now, I'm not really trying to graph anything. But then it's more than 2/3. So what do I need to do from 1/3? We have to go 2/3 in either direction. So if I go 2/3 either direction, 2/3 to the right is going to be 1. We're going to have a circle at 1, and 2/3 to the left puts me at negative 1/3. Now, I just circled there. What kind of dots do I need? It's just greater than, so they're open circles again. Where's my shading then? We're going out, right? Because it's all numbers that have a larger distance than that. Now, if you can get the hang of that shortcut, it is a quick, easy shortcut. If you have to think too hard about that shortcut, it's not worth the shortcut, is it? It's just as easy to solve. And so, if you want to test the solving, you can real quick. I mean, this would have been set up as the given, 3x minus 1 greater than 2. Greater than would be or, and so then it's 3x minus 1 less than negative 2. Add 1, divide by 3 in both cases. 3x greater than 3, x greater than 1, or 3x less than negative 1, x less than negative 1/3. Is that what I graphed? And it is. Okay, so it's one of those things where I'm trying to show you connections here. Honestly, there's nothing wrong with solving, but there's also something to be said for understanding. Excuse me. Okay, questions on that section? Okay, moving along then. Example B. See attached page for graphs of special functions other than below. I believe, is that the next page? Yes. And I will talk about those. I guess I could do it now a little bit. Here, I'll flip to the next page. Then we're going to do some graphing. These right here are just some special functions, and a lot of it is knowing how to deal with absolute value. Okay. One thing I do want to mention, you see the word cusp up there. Okay, that is a good calculus word. It talks about graphs of many absolute value functions come to one or more points called cusp, where the graph changes directionally suddenly. So we're used to our graphs having smooth curves, right? A cusp, like for instance in the absolute value b, where it is a hard turn, that makes a difference, because we'll talk about later in calculus how we won't be able to differentiate there. I know that means nothing to you right now, but give it a few weeks and it will. Okay? So, and just some examples. So like here is the line y equals x plus 2. You could graph the line x plus 2, yes? In this case, if you throw on absolute values around x plus 2, what that is saying, so the absolute value of x plus 2, we're trying to make the y value positive. So making the y value positive would take anything that is below the x-axis and flipping it up. And so that's why you see this little section right here flips up to be that section right there. Remember, a negative in front of a whole side reflects across the x-axis. So this is taking this graph here, putting a negative takes the whole thing and reflecting it across the x-axis. Okay, so just good graphing techniques. There's some sign here. So first graph on the second row is your sine graph. Starts at 0, 0, goes up, comes through pi, ends at 2 pi. If you do the absolute value of sine, the absolute value of sine is taking everything, all negative y values, and flipping them up. So now, my graph that normally goes up, down, they're all ups, right? What happens if you stick a negative in front of that absolute value? It's going to take the whole graph, reflects it upside down. Okay, what about a parabola? This is y equals x squared minus 2. So normally we think about it being a parabola that is moved down 2. Well, if you do the absolute value of that, what's the portion that's below the x-axis that needs to go up? That right there. So if you move that piece up there, there's my absolute value. Take the negative of the absolute value, reflecting it all across, right? We've got one more down here. This is an upside down parabola. So I know it's an upside down parabola because it has a negative x squared. You take the absolute value of it. Now we're taking the two side pieces and flipping them up. You do the negative of the absolute value, it takes the whole thing upside down. So those are just, helping you to understand how absolute value works, how to graph it by hand. And now I'm going to take us back and make us do some graphing. So this time, we're graphing the absolute value of negative sine x. Which, no, you cannot just say, oh, that's positive sine x. It doesn't work like that because we don't know what the x value is. So we can't just automatically make it positive there. Do you remember how to graph negative sign? Okay, it's a reflection of sign. So I'm going to, let's see. So anytime I do my sines, cosines, I break my graph into pi and 2 pi, and at least put the marks there, right? Not getting too official here. Just some basic review. Could you just graph basic sine? Do we have that knowledge? Basic sine, if I just do a pencil dotted line here, goes up above pi over 2, cuts through pi, down under negative pi over 2, cuts through 2 pi, yes? Okay. So what does negative sine? Not talking absolute value yet. Negative sine x, we said that was a reflection. And it's a reflection across the x-axis. And so that just means everything flips upside down. So now, instead of going up first, you go down first. So that is negative sine x. So I'm going to redraw my graph over here. Absolute value of negative sine x. What's going to change there?
The first part that goes below the
Okay. Anything that's below the x-axis has to become positive because we're looking for positive y values there. So that means now I go up first, we touch at pi, and then guess what? Whoops. We keep going back up. And so it's going to be repeated mountains as opposed to valleys. I don't know how you guys want to say it. Yes, I can scoot it over since I'm off the screen. Better? Okay, you got the idea there? Talk to you a little bit about absolute value. Okay. Next one. And again, I'm trying to get you guys to graph these by hands. Not that you can't grab the calculator and check yourself, that kind of thing. But there are times we can't use a calculator. So, A is y equals the square root of x. Do we remember what the square root of x looks like? What's y equals the square root of x graph look like?
Goes out like that.
Okay. Daryl just drew it in the air. I agree with this drawing.
Starts at the origin and just goes on to the right.
Okay, starts at the origin, goes off to the right. It's going to go through 0, 0, 1, 1, and 4, 2. I think of it as half of a sideways parabola. Sound familiar? Okay. That is also square root of x. Well, first of all, square root of x is only going to have positive values, correct? And what is that written with a power? Do you remember? Square root of x is x to what power? 1/2. Okay. And that's helpful to remember as well. Okay, B. Do you remember the cube root graph? First of all, if I write with a power, this is going to be x to the 1/3. There's a reason I'm talking about powers. It'll all come together on part C. Think about points if you need to. Or, okay, let me ask this. Can you remember what the x to the 3rd graph looks like? The one that curves through the origin there, kind of the snake-like. It's this one sideways. Okay. You can also put in numbers, right? If we put in numbers, we've got a point at 0, 0. What's the cube root of 1? 1. So we have a point at 1, 1. What's the next perfect cube? 8 is the next number I can take the cube root of, right? And the cube root of 8 is 2. So we have a point at 8, 2. Can I do the cube roots of negatives? Yeah, we can do cube roots of odd powers. What's the cube root of negative 1? Negative 1. What's the next perfect cube in the negatives? Negative 8. The cube root of negative 8 is negative 2. Okay, my graph was not great there. You know, I just realized Logan, I hope you're hearing me okay. Just dawned on me that I have been told. Helps if you get the right one. Logan, I'm going to put my AirPod in instead. I guess you can report to me later about the difference. But it just dawned on me that, I mean, I think he's probably been able to hear us decently, but he should be able to hear me a little bit better now. Yeah. Although now he can't hear your comments. Yeah. Although I'm not sure, you guys weren't real loud, so I'm not sure how many of your comments, other than Mallory's, you know, loud hellos, those kind of things. But we'll try this. He can report to us on the differences later. Okay. Did we get B okay? Yeah. Okay, C. Because I would like to think maybe A and B didn't come to you right off the bat, but once I drew them, we're like, oh, yeah, we've done those, we've talked about those, that type of thing. That's what I would like to think happened with A and B. Now, C. This is the one that I would say, yeah, probably not as familiar. The cube root of x squared. What is that as a power? X to the 2/3. Okay? How about if I write that slightly different even? Instead of x to the 2/3, what if I say x to the 1/3 squared? Is that true? Yeah. The power of 1/3 raised to the power of 2 becomes 2/3. So what happens, we know what x to the 1/3 looks like, right? X to the 1/3 is this fun thing. What happens when you square x values? The big thing that happens when you square something, positives stay positives, but negatives become positive as well. What's going to happen is this part of the positive part of b is going to stay as is. This negative part, kind of like absolute value, is going to flip up, because that's what a square does. It makes something positive. And so I'm not going to go into numbers, but I'm just going to give you a basic sketch here, in that it's going to be something like that, because you're taking this graph here and you're squaring it. And you square it, it gives it positive. I'm going to be cutting it close on time. We still have a lot to get done, don't we? Yikes. Okay, example 5. Here's another graph to be familiar with. Do you remember what this is? This is one of our 12, our infamous 12 from pre-calc.
Is this the one that looks like a staircase?
Kind of looks like a staircase, except the stairs aren't connected? Yep. That's this one. So, what this is y equals bracket x. Okay? So it's a bracket, or it's also int x, as in int parentheses x. I think when you do it on your calculator, you have to go into like your math menu and you have to find the function, the integer function, greatest integer function. You can't just take x and put a pair of brackets around it and expect it to work, because it doesn't. Okay, so let's draw this out real quick. These are the stair steps. They're just not connected. Let's see. I'm going to label up to 3 on the x-axis and down to -3. And then I'm going to go up and down to 2 and -2. The key is, if you know one piece of these stairs, you can draw them all, right? So the piece I'll give you is the piece that goes from 0, 0 to 1, 1. Has a closed circle at 0, 0, an open circle at 1, 0. And then if you recall what happens, that's obviously stop. We now jump, go straight above this open circle to 1, 1. At 1, 1 now it is a closed circle, connect over to 2, 1, which is an open circle. Is this sounding familiar? You can jump up to 2, 2. Closed circle, connect over to 3, 2, open circle. As I said, as long as you know how it begins, you can keep going. We can also go negatively. Down at -1, 1, -1, it's closed circle, connecting over to open circle at 0, -1. Closed circle at -2, -2. Open circle. There's another way to think about it. All your closed circles are at your repeated pairs. 1, 1, 2, 2, 3, 3, 4, 4. Okay, so that was one of our 12 last year. Moving along. Good news is once we get down into logs, those will go pretty quickly. But I know, as I said, I'm realizing all of a sudden we are going to be close on time. Example 6. Write an equation for the function whose graph is shown. This is called a piecewise function. Because is there an equation that represents that exact graph? No. That is 3 different pieces put together. Calculus likes to use piecewise functions. So understanding how we put all this together to create one piecewise function is going to be important. So what we're going to do, this is going to be the idea. You've seen piecewise functions before. Do you know what I mean? When it's like y equals, and there's different, it could equal x, it could equal x plus 2, it could equal 3, it could, whatever it is. So what we need to do is figure out what the different equations are. Okay, so let's pick a piece here. You guys want to do that middle piece maybe? If you think about this, the angled piece here, ignore the flat pieces. But if you were to extend that angled line, what line is that? What equation works for that? Can you figure out what I'm talking about there? What'd you say? Y equals x minus 2? Is that an agreement? So this portion right here is y equals x minus 2. That's y equals x minus 2 between what x values? Here at 1 and at 3. So that is the middle piece of our piecewise function. Do you want me to go ahead and write that in?
Yeah.
This is the middle piece. So I'm going to have a piece above it and a piece below it. So I'm going to write x minus 2 because we already have y equals, right? So the equation y equals x minus 2 for what x's? X's that are between 1 and 3. So I'm going to write that as 1 less than x less than 3. We'll come back here and talk about in a moment whether those need to be equal to's or not. Okay? Now, pick another one. We have to do our 2 horizontal pieces. What about this line right here? What is the equation for that line? Y equals -1, because horizontal lines are y equals the number. And so this is y equals -1. Now, that is, so I'm going to put that as my first piece, my top piece, because as we go left to right, it was the first one. So it's just -1, because again, it's y equals -1. For what x values? From 0 to 1. Does it go to the left of 0? No. So I'm going to say 0 less than x less than 1. Now, I haven't been putting the equals to in. At 0, though, you absolutely could not put equals in because it's an open circle. The other two could go either way here. Let's finish off this last piece and then I'll worry about them. What's this horizontal line here? What equation is that? It's across from 1. If we extended it, it would cross 1. So it's y equals 1. So my bottom part is y equals 1. For what x values? It starts at 3, and then notice there's an arrow. So that means, so I'm going to write it as x greater than 3. Now, officially at some point, we need to put 1 and 3 because those are the overlapping pieces. Back to me, computer, in a category. The 0 cannot be equal to. Usually you don't put equal to 1 on both pieces. I didn't catch it in time, did I? Enter the password, then hit enter. Okay, so officially you can't really have 1 defined both places, although in this case doesn't matter. It's the same point in both cases, isn't it? So honestly, it doesn't really matter, but I would say pick one. I'm going to pick putting the 1 right there. The 3, it's in both categories. It's the same point in both places, isn't it? It would matter if we had a separation there and they were in 2 different places. Again, I'm going to put the equal to 3 right here. Officially, those 1s and 3s could be on the other part. It wouldn't matter either way. Okay. You've seen piecewise functions. You've probably never written a piecewise function. But it's breaking it down into each piece and then putting what interval it's on there. Questions on that? Okay. Here we go with logs. You learned logs in Algebra 2. I don't know if you learned them in Algebra 1 or not. Algebra 2 definitely, but form of a logarithm. Log, forget which way it is officially. I've read it both ways. Log base b of n equals L. If you recall, do you remember the phrase? Left, right, middle. If your log is on the left, you can change it from a log equation to an exponential equation, where left, right, middle. So b raised to the L is n. So left raised to the right equals the middle. B raised to the L is n. Sound a little familiar? We did this in pre-cal as well as Algebra 2. So write 4 equals 5 to the y as a log. Meaning I want log base something of something equals something. Now, if you're struggling, could you reverse the given statement? And if you don't need to, don't bother, ignore me then. But if it works better for you, you can reverse it and put the power on the left there. Log base what? 5. The base of my exponent is also the base of my log. Log base 5 of what? 4 equals y. I tend to, besides just left, right, middle works great going from log to exponent. To go from exponent to log, I tend to think my base of my exponent is my base of my log. The y and 4 flip-flop to be 4 and y. Come up with what works for you. Okay? Base 10 and base E. Logs that use 10 as a base are called common logs. That's your log button on the calculator. Logs that use base E as a base are called natural logarithms, and that uses the ln. Remember, ln could be written as log base E. Now, it asks us to write 2.4 as a power of the base 10 for part A and E for part B. So we want to take 10.4 and write it as a power of base 10. So what that's saying is 10, we want to know 10 to what power is going to equal 2.4. And that's your easiest way to start it off. The book uses L. So 10 to the L equals 2.4. So write 2.4 as a power of the base of 10. So 10 to some power equals 2.4. I want to know what L is. What? Okay, so if we undo this, we take it out of exponent form into log form. It's log base 10 of 2.4 equals L. So you're undoing your left, right, middle. Can you find L at this point? With your handy dandy calculator? What is the log of 2.4? It is not red, if that's it. It's not bread either. But I am hungry for lunch.
0.3802.
Okay, I'm going 0.38 for this. I guess I could go more than that officially. So now, if we go back to our original statement, write 2.4 as a power of base 10. So 2.4 is approximately 10 to what power? 10 to the, what I wrote as 0.38 number. We do the same thing for part B, except instead of using 10, we're going to use E. So if we want 2.4 as a power of base E, that means E to some power L has to equal 2.4. Undo your left, right, middle. Now, you can write log of base E of 2.4, but really better to say natural log. Natural log, which is base E, of 2.4 equals L. And of course, can you use your calculator to find what L is? L is the natural log of 2.4, which I've written down as 0.88.
Yeah, 0.875.
Okay. So if I'm going to rewrite 2.4 as a power of base E, 2.4 is equivalent to E to the 0.88. Okay, so a trick there to connect your logs and your bases. Okay, bottom section. As long as we get some of these done, we'll get you in the right area. It says simple log problems. They all have logs in them. What's our phrase? Left, right, middle. Or when Mrs. Sargent writes LRM. So, solve log base 1/3 of P equals 2 for P. How do I get it out of log form? Left, right, middle. So, what's this going to read? 1/3 to the second equals P. Geez, that's pretty easy solving. What is P? 1/9. If only they were all that easy, right? Okay, example 10. What's left, right, middle say? X to the second equals 6x minus 9. How do we use our algebra skills to solve this? Okay, equal to 0. So I'm going to make it x squared minus 6x plus 9 equals 0. Factor. What's this factor into? X minus 3 times x minus 3, or x minus 3 squared. Set both parts equal to 0, and x is 3. Okay, example 11. Log base b of 9 equals negative 1/2. What's my left, right, middle say? B to the negative 1/2 equals 9. Here's my suggestion since we're running out of time. What power can I raise the left side to that would essentially eliminate the negative 1/2 so that I will just have B? Power of what? Except I don't want to use positive. I want to use negative. Okay, so his comment was 2 over 1 because he's using the reciprocal, right? The advantage of using a negative 2 is we're going to be doing a negative times a negative. Right. So the idea here is if I raise this left side to the power of negative 2. Well, what's the idea in the equation? Whatever you do to the left, you do to the right. So if I raise the left to the power of negative 2, raise the right to the power of negative 2. On the left, when you do power to power, you multiply. Negative 1/2 times negative 2 is just b to the first. 9 to the negative 2. What's the negative tell me to do? Take it to the denominator. So 1 over 9 squared, which is 1 over 81. I think Daryl had already said 1 over 81. Maybe you haven't thought that way before, but that wasn't, I don't think of that as horribly difficult. We do other stuff that's much more difficult than that. So, example 12. 3 to the 2m plus 1 equals 1/27. Here's another skill. It's been a year. We've slept a lot since then. I have a base of 3 on the left. What I need to solve for is in that power. Yeah. How can 1 over 27 become a base of 3? What do you know about 27? It's 3 to the third, right? Because 3 times 3 is 9, times 3 is 27. Because it's in the denominator, that is 3 to the negative third. So if I have 3 to the 2m plus 1 equals 3 to the negative third, remember if the bases are the same, you can drop the bases off, set the powers equal to each other, and you can solve. 2m plus 1 equals negative 3. Subtract 1. 2m equals negative 4, and m is negative 2. Okay. That was perfect time. It was a long lesson. Unfortunately, we have some of those. And other times we have really quick lessons. So, yeah, I think today would have been a long lesson if Logan was here or not here. So, hopefully Logan got something out of that too. Lesson 9 for tomorrow, please. Page 60 is what I have written down.